Here I will discuss the trapezoidal method, which is yet another numerical method for integration. So similar to what we've done for the rectangle method or the midpoint method in the previous video, we can investigate the trapezoidal method by first looking at, well, this end form that we want to accomplish, so a weighted sum of function evaluations at specific points x1 to xn. And then we can see how the trapezoidal method works by first investigating which points, which evaluation points are selected here, and how these weights are determined. So first looking at these points, well, for the midpoint and rectangle method, we used 1 point, and here we will use 2 points. So 2 points are used, and those points are the endpoints of the integration interval, a and b. So the trapezoidal is a closed integration method. This will result in an integration rule, which then henceforth looks as follows. So we have a weighted sum of f evaluated at the left side of the integration interval and f evaluated at the right side of that integration interval. All that's left for us to do now is to determine these coefficients C1 and C2. So in order to determine those weights, again, we follow the same approach that we did for rectangle and midpoint rules. We have 2 points here, and between 2 points you can draw a single line. So that's exactly what we do. Well, we approximate f on this interval AB with a first order polynomial. So that means with a line. And there are several ways in which you can write this line down mathematically, but this is a common way. And you see that if x is equal to a, then this polynomial will be equal to f of a. If x is equal to b, then it will be equal to f of b. And everywhere in between, it's a weighted, well, it's kind of a combination of fa and fb. So that's the line between those 2 points. So now that we've done this, well, we can take a look at the actual integration. So we want to approximate this integral, and we swap out this integrand, which we cannot integrate or which is very hard to integrate, by a polynomial function. And polynomial functions, well, we just plug in this guy over here and obtain this. And this is fairly easy to integrate. And by some simple algebraic manipulations and some simplifications, you end up with this thing over here, which is then the trapezoidal rule. Because actually, this formula, if you remember formulas for shapes of different for areas of different kind of shapes, this is the area of the trapezoid described by this point, this point, this point, and this point. So that would be this formula, that's the area of that trapezoid, which also corresponds to it being called the trapezoidal method. Also, again, we can, if we're not satisfied with the accuracy of the standard trapezoidal method applied to the full interval in one step, we can try to increase the accuracy by using a so-called composite trapezoidal method. And in this composite trapezoidal method, what we do is we subdivide the interval from a to b in n subintervals of width h. And we say, well, the total integral from a to b, we approximate it with these blue areas over here. So we compute the area only for the subintervals, and for the subintervals now we will use the trapezoidal method to compute the areas of each of these blue areas. And you can apply the trapezoidal rule to the first to I1, and you see that that will be equal to FA plus F at x2 divided by 2 times h, and that is exactly this trapezoid, the area of this trapezoid, that is equal to I1. And you can continue to do this for each of the subintervals as well. So summing this all up, well, this ends up with the following formula. And this can be simplified a little bit because a straightforward implementation of this, well, this would be one, two evaluations per term in the sum. So this would be a total of 2n function evaluations. And if f is expensive to evaluate, you obviously don't want to evaluate it any more than strictly necessary. So you can actually write this out a little bit, and then you can actually find that except for the endpoints, so except for f at a and f at b, you find that all the other function evaluations, so from x2 to xn, all those other evaluations come up twice. So if we recast this a little bit, we can find that this sum can be rewritten as this one. And you can count the amount of function evaluations here, and it's actually 1, 2, plus n minus 1. So that's n plus 1 function evaluations only. So this is the appropriate form of the composite trapezoidal method that we can then also use. Now, before we apply the methods that we've seen so far to a practical example, here I just want to quickly recap the methods that we've seen so far. So to reiterate, the idea that we want to do is we want to approximate the area below this curve, and the exact area is equal to the definite integral of f between a and b. And we've seen different methods. Left rectangle, in which we simply draw a rectangle with the left-hand side end of the interval, x is a. The right rectangle, we do the same, but with x is b. The midpoint, which is also resulting in a rectangle, but seems to attain a better accuracy, at least from a qualitative point of view on this graph here. And we'll try to make this a bit more quantitative in a few minutes. And we've also seen now the trapezoid where, well, we draw a line between FA and FB, and then we can use that to compute the area of this trapezoid over here using this formula. Also for each of these methods, well, if we're not satisfied with the accuracy that we attain over the full interval, we can try to increase the accuracy by reducing, or let's say by splitting up the total interval into smaller and smaller subintervals and then summing up the individual areas of these subintervals. And this led us to the composite rectangle rule, the composite midpoint rule, and the composite trapezoid rule. And well, these formulas, they look somewhat complicated, but we've already seen that it's not so hard to implement them. But when I think of numerical integration, I always find it very helpful to make these geometrical pictures in my head, because you see, it's really, this is basic geometry, and it's the ideas behind numerical integration are often nothing more than just computing areas of shapes that we know how to compute and using those to approximate such a shape that we do not know how to compute the area thereof. Okay, so let's look at an example. And the example that we want to investigate here is we have an airline or a plane which has landed, and upon landing it will deploy its thrust reversers in order to brake. And that's how airplanes brake. They reverse the thrust of their jet engines such that they have some kind of braking force which allows them to decelerate. And the speed of the plane, or the velocity of the plane, can be written using this differential equation. So we have a plane of 97 tons. And this is basically Newton's second law, somehow recast. And we see that here in the right-hand side, well, this would be actually a model for the force enacted by these thrust reversers. We have an initial condition. So at the point of landing, the airplane is traveling at 93 meters per second, after which it starts decelerating. And the question is, we want to find the position for which the velocity at that position is equal to 40 meters per second. So what you want to do is, well, you want to solve this ordinary differential equation for v, which is a function of x, and then we want to find x such that v at that x is only 40 meters per second. That's what we try to do. So yeah, actually this is an ordinary differential equation, or an ODE. But one of the ways in order to solve ordinary differential equations analytically, and we will learn how to solve them numerically in the next chapter, but this one turns out to be that we are able to solve it analytically by separating the variables. And if you do that, well, what we actually do is, well, we throw this dx to one side, and we group all the terms with v on one side. And then what you can do is, well, you integrate over the appropriate interval that you want. So a straightforward manipulation of this equation will give you that dx is equal to mv divided by this times dv. And then we know, well, if we integrate this dx from 0 to the desired x star, that v at that point has to go from 93 to 40. So it is on both sides we apply integration, and it's not very important how we do this derivation. It's more kind of an example at how we can use such integrals for practical problems. But the main thing here is that this problem boils down to trying to find the numerical value for this integral over here. So this function, f of v, this fraction, we want to integrate that from v is equal to 40 to v is equal to 93. And we can actually do this by hand. So if you do a substitution, so we just substitute the denominator over here, well then, and you also apply the substitution to the integration bounds, well then this becomes an easy integral. This is becomes a natural logarithm of u. And we can compute the exact value of this integral up to 4 decimals, which is 574 meters, 0.1494. That's just the exact value that we want here. So this is just to kind of set the scene for this problem. But what we actually want to do is we want to use our numerical integration methods that we've seen before in order to approximate this integral over here. So in the previous slide, we already saw the exact value of this integral is 574.1494. And we can actually plot this function f of v. So between 30 and 100, it's plotted here. But what we're actually after is this shaded blue area here. So the area below f of v for between v is 40 and v is 93. And so we want to use our numerical integration methods to approximate this area. So let's give it a go. Using left rectangle rule. Well, what does that mean? Well, we would evaluate f at v is 40 and simply multiply that with the width of the interval, so that the area approximation would be equal to the rectangle that I'm encircling here using this pointer. And we see that, well, for such an increasing function, the left rectangle rule leads to a gross underestimation of this area over here. So this left rectangle rule, well, basically it's worthless. It's very, very inaccurate in this case. A similar thing can be seen if we do this for the right rectangle rule. So the right rectangle rule, just to recap, we evaluate f at the endpoints of the interval and then multiply that with the width of that interval. So that would be the area of the rectangle that I'm encircling now with the pointer. And so this would be 780 meters. So a gross overestimation of the blue area in the graph, actually. Let's have a look at midpoint. So for midpoint, we evaluate f at 40 plus 93 divided by 2, so that's roughly here. So in that sense, we would use this as a height for our rectangle. And we see that for this function, this already leads us to a numerical number which is relatively close to the exact number. Well, this is still 3 meters apart. You wouldn't really want to use such an accuracy when you're doing vital, for instance, safety calculations or so. But as a first estimate, this is already quite good, this midpoint rule. And we can also take a look at the trapezoid rule. So that would mean that we draw a line between this point that I show over here now and the point here at the top right and compute the area of the trapezoid. And again, this is much better than left rectangle and right rectangle rule, but it's still not very accurate. So I would say from our standard integration methods, we don't get the accuracy that we would desire. However, I also mentioned this before, but we can use these kind of composite methods when we want to increase the accuracy of our integration, of our numerical integration. And I already showed how to implement this, for instance, for the midpoint rule or the left rectangle rule. And here just I show it again for the trapezoidal rule. So what we would do in the trapezoidal case, we want to implement this formula over here. This is very similar to what we've done before. The only difference here is that we have a slightly different formula over here. So we again define what h is, define these points xi, we compute f at all the necessary points, and then we basically just plug in this formula over here. So this is really very basic programming that allows us to implement such a composite trapezoidal rule in the in MATLAB as a function. Now let's take a look at some results from these composite methods. What we see here is, well, we have the left rectangle composite method, right rectangle composite method, midpoint and trapezoid composite method. And we have here the number of subintervals that we used in order to approximate this blue area over here. So the first thing that can be noted here is that for one subinterval, well, these composite methods, they obviously are completely equivalent to the standard non-composite methods for which do this integration in one step. So that all makes sense. Let's take another look at this. So for both left and right rectangle, well, we start increasing n more and more and more, but only very slowly we start getting some accuracy in the approximation of the area that we have over there. For instance, well, let's say that we really want to use this left rectangle rule. We do 100,000 evaluations, then still we are only accurate up until, let's say, 2 decimals after the comma. Whether that's accurate enough obviously depends on your application, but 100,000 function evaluations, if your function is pretty, in this case it's not expensive to evaluate, but if it were quite expensive to evaluate, so if, let's say, it would take 1 second to evaluate that function, then computing or approximating the integral with this left rectangle rule, well, that would be approximately 100,000 function evaluations. That would take you approximately 30 hours. So that's not something you would want to do if you can avoid it in any way. And a similar thing holds for this right rectangle rule. Even for 100,000 subintervals, we're not very accurate still. We cannot achieve this exact or approximate this exact value up until 4 decimal numbers. For midpoint and trapezoid, however, we see that even for one subinterval, and that's already what I said, well, we are quite okay. It's not very accurate, but it's quite close. But as we increase n, we see that already at 1000 subintervals, we have the same numerical value when rounded to 4 significant digits after the comma as the exact value. So also this exact value is not exactly this, I just rounded it to 4 digits. And a more detailed error analysis will come at the end of these set of video lectures. But for now, what I want to stress here is midpoint and trapezoids. Well, they are more accurate by themselves. But if we start using them in composite rules, well, their error seems to go down. They seem to approximate the true solutions much faster than this left and right rectangle rules. In the next video lecture, we're going to see whether we can come up with even more accurate methods by using higher order polynomials. So in left and right rectangle, but also in midpoint, we approximated the function f with a constant or a 0th order polynomial. In trapezoid, well, we approximate the function with a line or a first order polynomial. And in the next video lecture, we'll actually see what happens when we approximate the function with quadratic and cubic polynomials. And that's what's called the Simpson's integration methods.